Okay, now we will start the hands-on programming session, and I will start from like very, very basic coding. So right now I have a file open. It has nothing in it. So I will start from here. And so basically the first task, if those of you that are more experienced can go on, don't wait for me. You already try. So the task is to do this. So create a set of points distributed. You can either do 2D or 3D. It doesn't matter at this point because this doesn't really depend on the dimension, this very simple one. But maybe in the future, you will eventually want a 3D code, so you can start from 3D. What you want to do is create a set of points that have four attributes. It has X position, Y position, Z position to determine where it is in the space, and Q. So it has four variables, X, Y, Z, and Q. You need to create a set of points that have different X, Y, and Z values, and Q you can have all ones, or you can have them different values, or it doesn't really matter. But as long as they're not zero, it's fine. So you can have any value of Q. You want to generate those points first, and you want to generate another set of points that have either a much larger X value or much larger Y value or much larger Z value, so that it's far away from these set of points. Once you have these two boxes, you first want to calculate the center of the box. So if you already have a plan on what your coordinates are going to be here, then maybe you can distribute your particles around point 0 and then say that the center of the box is at 0. And for this one, you can distribute all your points around 5 or 10 or something, and then say that your box is at 5 or the center is at 5, 0, 0, or some location in the 3D space that is close to these points. Once you have that set of points, you want to calculate the sum of Q, all the values, and say that that's the Q here. And then you want to take that Q and calculate this equation here, which is, so you need to take the distance in each direction. So if you had xi minus xj, and yi minus yj, zi minus zj, each of those components you need to use to calculate the distance. So from that you can calculate the distance r from each of the coordinates, and then you divide q by r to get the u value at this point here. And then you just assign the u to all the points. Oh, maybe I should use the stick. Yeah, so you calculate that to use the point to assign the values to all the points here. And then you need to do an extra calculation to check your answer. And that calculation, you need to loop over all these points here, loop over all these points here, and try to calculate the ui. For all the ui's, you want to calculate the effect from all the j's. So it's a double loop, looping over all the I points, these are the I points, to get all the ui's from the effect of all the uj's. Okay, so since the points are far away, this distance will never be 0, so you don't have to worry about 0 divide or anything like that. In the future, when you start to calculate the whole domain against the whole domain, you will have to worry about the case where you're calculating for the same point, because when I equals j, this distance will become 0, and if you divide by 0, this number will be infinity, and you won't get an answer. So you'll have to worry about that in the future. But in this case, don't worry about that. The points are always far apart. So this will never be 0. Okay, so just loop over all the points against all the points and get the ui. compare that UI against this UI. You can either print all the numbers and see what they look like, or you can take a more, like a mathematical representation of, take like the norm of the difference, so subtract all the values for each I, subtract this U from this U, and then, take the square of that and sum up all those squares and take the square root at the end. That will give you like a standard deviation of the difference between the two. And if that number is large, then that means the error is large. You can divide that by the absolute value of U so that you'll get a relative norm error. But anyway, you can calculate the error of this approximation. And an interesting thing to do once you've done that is to change this distance, make them very close and see how bad the accuracy gets. Make the distributions far and see how good the accuracy gets. So first, we will do that first, okay? You can ask questions anytime you find something strange, or I won't be making any mistakes on purpose, but I might still make mistakes. So tell me if you see something wrong on the screen. And okay, so I will proceed with the coding, and you can follow, or you don't have to wait, but you can actually confirm by checking your code with mine. Okay. Okay, so maybe it's you have like a maybe I can put it here. Okay, so I'm just going to add, basic header files because I'll be doing standard lib and maybe I'll add math.h. Okay, these are just including header files. Okay, now I'm going to write the main function. Well, just to check if your environment is working. Yeah, why don't we write a hello world for those of you who haven't been programming for a long time? Yeah, that's okay. Yeah, I'll just do it like this. Okay, so let's see if this works. Oh, it's fine. Yeah. Okay, so let's try to compile. So the name of the program doesn't really matter. I just named it step1.c. Okay, it compiled. Now I'm going to run a.out. It said hello. Okay, so well, I'm sure everyone can do this one, so I won't go around to check this one. Okay. So now let's generate a set of points. Okay. So let's generate 10 points. Okay. So we have x, y, z. I'm just creating arrays for create x, y, z, and q. Okay. So now I'm going to loop over from I to n. Yeah, why don't I actually print what I'm writing? So I'm going to say xi equals, let's say, some random number. So I'm going to use a random number generator here. that generates a number from 0 to 1. And I'm going to print that. Okay, just so I don't disrupt whoever is looking at my screen, I'm going to split my screen. On this side of the screen, I'm going to try to compile what I just wrote. Okay, so you can see what I'm coding. So I'll be switching between these two screens and adding more things. But just for those of you who don't know, who have. Oh, thank you. Okay, yeah, thank you. So if you've never used this DRAND48 thing before, this is I've printed so that you can see what it's doing. It's generating some random numbers between 0 and 1. So you don't have to do the standard RAND thing generates an integer and you have to divide and do things, and this one is much more useful. So I'm using DRAND48 to generate a number from 0 to 1. Okay, so now I'm going back to this side of the screen and going to do the same thing for y and z. So DRAND48 and DRAND. Okay, and by the way, I'm using the editor Emacs, but you don't have to. You can use whatever editor you want. Oh, okay. And so just to explain everything I'm doing for, people with different levels may not know certain things I'm doing. So this printf LF means double. So if I wanted to print a float, I'd do %f. If I want to print a double, I do LF. And I'm going to print X, Y, and Z, all of them now. Okay, so I'm going. So now I'm printing X, Y, and Z, 10 numbers. So these are my X, Y, and Z. Okay. And maybe I'll generate Q as well. Q, let's say I'm going to make it all ones because it's easier to check if they're all 1. The sum should be 10, and it's easy to check if it's correct. So I'm just going to make them all 1. And, oh, okay. I forgot to add another LF. Okay, at some point I'm going to go around checking if everyone is okay, but right now I'm just going to go on and create the second set of points. So let's say I'm going to do I'm going to create xi, yi, zi, qi, and like a second set of points that will be far away. So I'm going to call them xi, yi, zi. So I'm going to use two different variables for the. Okay, so let's call these qi
And now let's create a second set of points, xj, yj, zj, and qj. Well, actually, for one of them, I don't need the q. Let's say for the I don't need the q. Let's create ui, and ui can be initialized to 0 or something. Okay, so now everyone should have random x, y, and z for I. Okay, now, but this is not good because I needs to be far away. So I'm going to add some number here. Let's do like 10 or something. I'm going to add 10 to xi so that it gets shifted far away. Okay? Okay, so now we have all the set of points we need. We will do the first calculation. Let's loop for let's use j just to be consistent with the, I'm using j as the loop counter, so it's easier to see the correspondence between the lecture. Okay, so I'm going to create a new point. So let's say xj prime I call qjp. Okay, so I do need to create a new set of points. So let's say xj prime, yj prime, zj prime, qj prime, and also the xi. Yeah, I need to create for both I and j. Oh, sorry. I prime. Okay, I created all these different values, and let's say, so since I'm using a random number generator from 0 to 1, the center for these boxes we should know. So xjp I think should be at 0.5. Well, actually all of these things should be at 0.5. yj prime, zj prime, and for the I, only xip needs to be like 10.5, and yip and zip are still 0.5. Because I shifted xi 10, so the center of the box should be shifted 10. Okay, now I'm going to do the summation. So I'm going to start with qjp equals 0, and then I'm going to add all the qj's. So qj, j. So this will add all the qj's into qjp. Okay, this is step 1. Maybe I should write it somewhere. So this is step 1 in the slides. It adds all the qjp. Maybe if I have enough room in my screen, I can show. Yeah, so step 1 was to add all the qj's. So that's what I'm doing, and adding them to qj prime. qj prime is not an array because there's only one number, 1 point. So it's just one double, not an array. Okay, now step 2, we need to calculate ui prime from qj prime divided by, yeah, so to calculate the distance, maybe we should create some more variables like dy, dz, and r. Okay, so what I'm doing here is I'm trying to form dx is the distance between dip minus, oh sorry, xjp dx dy dz dx dy dz, like this. So I'm calculating the individual distance in each direction, and then from this I can determine from the square root of the, you know, like square, square, square. Yeah, so this is the definition of the distance, right? It's the square root of the distance in the x direction squared, y direction squared, z direction squared. So this is how I calculate r. And then I just divide by that r. This should be step 2, calculating uip from qjp. Okay, now step 3 is just saying I loop over I to all endpoints and say that ui at point I is equal to uip. Okay, this is step 3. UIP we just calculated in step 2, so we just now substitute that to all the UIs. Okay. And now we need to check the answer by looping over all the points. So I goes from 0 to n minus 1, and we have another loop that goes from j 0 to n minus 1, and we need to calculate the ui. Let's call this UI direct or something, UID. Okay, so UID, we just calculate that original equation. Okay, so again, I'm going to use the dx, dy, and dz. dx equals xi minus xii xjj dx dy dz is like this. X dy dz equals xi minus xj, and then I'm going to use this definition of r again, and then now it's easy. I just need to divide by r like this, and this is each of my UIDs, and the sum of all of these should match. So now let's do a print and see if these two numbers, how close they are. So what I'm going to do is I'm going to print UI that we calculated through the 3-step procedure, and I'm going to compare that with the UID that we just calculated with the direct summation of the original equation. So these should match. right? These should be the same number. So I'm going to shift back the screen. I'm going to keep showing this screen so that you can see, but I'm going to now compile on this side and see what happens. Oh, I think I forgot to define UID. Yeah, I had to do a declaration of the variable first. Oh, UI I also didn't define. Or no, I did define it. There seems to be some... Did I define UIP? Did I define... I defined UI up here. No. Ah, this one. Yeah, okay. Okay, this had to be UI. And this one too, I need to... Okay, now I think it's good. Okay, yeah, now it compiles. Okay, so now I see similar numbers. So what I'm comparing is this side. This side here is the one you get from the 3 steps. So they're all the same number because you just assume that they're all the same. But if the 2 boxes are far enough, the actual solution is, very close to all being the same anyway. So it's still a good approximation. They're separated by 10. So I shifted x 10. So this is like very far away. But so now, if I change the distance, then the numbers will start to become very different. And let's see. So this number I will change to maybe 5. I also need to change here to 5. Okay, they're still quite similar. So maybe I can do more. Why don't I just change this into a variable so that I don't have to change 2 places? Okay, so now I'm going to change this distance to 2, which should make the solution quite inaccurate. Yeah, so now you see quite some are like 6, 4, but the others say 5. It's somewhat like an averaged solution, but you start to see this big difference. Now 2 is still not the closest it can be. So we have from minus 0. We have from 0 to 1, and the other is starting from 2 and going to 3. So yeah, maybe this is the closest it can get. But so we want to improve this accuracy with high order expansions eventually. But for now, I think this is a good way to see how this approximation can work. So, it's roughly 5. We're getting a rough answer. That's roughly correct. Okay, so is everyone able to get this to work? It's
That's local.
yeah. I guess maybe I went too fast. No. No. Are you able to log in somewhere? No.
We do not have to write the Linux language. So
Ah, okay. You want to use MATLAB? You have MATLAB. You can. Yeah. You can. Yeah, you can try to do it in MATLAB. It should be the same. You can do the same thing in MATLAB too. Okay. How? Okay. Oh, this is something else. Yep.
Show the code in the little bit.
Here? Step one. Step 1, 2, 3, like this. Okay. Okay, so I think everyone is coding something. Yeah, okay. Okay, I'll see. We have time, so I'll go slow. Make sure everyone is okay. Okay. Oh, okay. Okay.
London just also a zero.
The London did not show London.
Oh. What happened? No random? No, it shows 1. It's always 1.
I used one plus, but
Oh, it's showing 0.
yes.
Understand it. Oh.
Is anything wrong here?
Maybe it's Ubuntu. Oh, that's strange. This is double. Okay, it's. Okay, so sometimes you need, so this is called a seed. So srand48 sets like a random number seed, and sometimes you need to set this for the generator to work correctly.
So if I need for P London,
No, you only just need to do this one time in the beginning. So it should be, yeah, sometimes you need to do this. Oh, okay, so I have some. Is everyone?
I will prepare the account for them.
Oh, they have account. Okay. Okay, yeah,
I think
let's.
most of them can compile locally.
Locally,
in their own,
okay.
Computer.
But maybe some.
Maybe some need that.
Yeah. Here, okay. Yeah, maybe on this side I can show other parts of the code so that you can.
Okay, that's good.
So I can show a larger part of. So step. Maybe.
Some people they include a math
Hmm.
large, but still they didn't get a square root.
Oh, really?
Do you have any idea? I think probably they haven't installed the
Math.
Bible correctly.
Let's see.
如果你那个 square root SQRT 好像如果 include 进来的话，你来一下那个server 账号，移到 server 上去问好不好？那你看看是不是你当初装的时候，或者用 ESQRT。
You can try square root f. No? Do you have it?
Square root f, not your s.
There's d square root. No,
No, they
that doesn't work.
no.
You can try sqrtf.
Oh,
Sqrtf. There might be a sqrt.
yeah.
No? No.
Interesting.
Do you have math?
Yeah, I think he did.
Okay. Cool. GCC. Oh, that's strange. Undefined reference to it. No, I don't know what's wrong.
Yeah. I think it's probably the how do I compare Chinese to no try to say 我减 L M 那个我那个卡帕里面是减 L 的。那个如果你卡帕不过的话，你 GCC 空一个 dash L M 再空一个，然后 step 1点是 some old version
Yeah.
they need to put the flag dash L M.
Ah, okay. Yeah. I see.
画的，老师你是说 dash
对 GCC 空一个对，就是 L， 然后你要打那个 step 1点是。
还是别
这是 B 还是
L
没有用，工作站上才可以，工作站上需要打 LM， 不然没有。
工作站需要打 L。
对
OK。
所以
他们就是有过，但是也可以过了。OK， 那有的好像可以，有的不行。那如果不行，
我再找他。
有同学到工作站上已经，
我现在是在我自己台上，
还是过不了。
对，我现在是我在自己的市场，所以我应该去用那个账号。
呀，那就用这个账号。
因为我自己跑不动，我这跑不动啊。
账号有一点
打在后面。
你说是打后面？
对。
好，那有点。
那个不知道工作站密码的，工作站那个 IP 或者那些下手。
要不然他有一种办法就是说他先打这个东西。
So this problem is solved
Okay.
by using LM,
LM.
but there is, but he used a server, so it's okay for now.
Okay.
所以你就可以 OK， 要
我打在后面的可以。
啊？
我的副有没有在后面？
在后面。
这个工作站下面。就是对，直接把这个东西对。
哦，well, it's orders interesting. If you put a dash behind, then it's work.
Ah, yeah.
哎，那个玉阳，
哎，
那个
打在后面吗？
打后面。
OK，我试一下。
然后你的城市点是空
Good. Okay. Everyone's okay. Okay.
我有 bring 它，还是我关掉重开？知道吗？扣的哦。白痴。谁叫 X 扣？
但是你至少可以。
你叫我看一下。啊，我先传给你。在哪里啊？
好，那这边尽量做。
Okay. Okay. We should we continue or we can take a.
How many hands-on session you plan to do?
So we can take a break and then continue until 1.
Yeah,
Yeah,
I
yeah.
think that's a good idea.
Okay. But
这
I
样子为什么？
well if everyone is finished up to here, then maybe I should continue now, so they have more time to work. Yeah.
That's also
Okay.
A 点号是你如果要给干的话，你后面要再多给 option。
哦，所以我是想说。
好。那这部分还可以吗？他 就至少有没有看懂老师做的？可以好，那我们就先继续好不好？好
Okay. So next is let's see. Okay. So now we are running just like this and seeing numbers for when they are far away. Okay, the next task is this one. So now we're just doing only like this one and this one, only one pair that's far. In the next one, what we want to do is divide the domain into many different boxes. Or actually what we can do is we can create this artificially. Like create a box that has from 0 to 1, 1 to 2, 2 to 3, and 3 to 4. And like create a artificial domain that looks like this one. And then what we need to do is we need to make the far pairs interact, and then the near pairs interact directly. So what would be the best way to do this? I think we can number the boxes. So the picture is in 2D, but actually we are now working in 3D. So you will have 4 by 4 by 4, 64 boxes. So you want to create 64 boxes, each with maybe 10 points. And then you want to calculate this thing, and then also calculate this thing. And the question is how to determine this box here, and how to determine these boxes here. So usually what we do in FMM is we have a numbering scheme. Yeah, why don't we do this? We can number these boxes with 3 numbers. So in the x direction we have, this one is 0, and in the y direction this one is also 0. And so we number them 0, 1, 2, 3, 0, 1, 2, 3 in each direction, and we can have 3 numbers being assigned to each box. That way we can just loop over each of the box numbers to find a particular box. That would be, I think, the easiest way to find which boxes belong to this group and which boxes belong to this group. So yeah, maybe let's do this incrementally. So first, I think we should do the box finding program without the calculation, because this, if you add all the calculation, it becomes complicated. So what we want to do is to do like a box finding algorithm that finds this one, the near field, and the one that finds the far. So like a box finding program. So let's try to write a box finding program. Okay, so let's open a new code. So let's say maybe we should copy step1.c to step 2. So now we have step 2. Okay. So now I'm opening step 2. So this function is step 2. And I will leave the previous code. I'm going to continue after the previous code because I'll be using this previous part anyway. So now, how do we do the box finding? So let's say we define the box number. Let's say oh, I know what. Let's not create any boxes. It's maybe it's easier if I. So here's what we'll do. We just create the same. We use the same distribution we are using now. We just create many copies of them. This is much easier. So what we do is say that this is from 0 to 1 and 0 to 1. We just move this one in this direction 1, and then the coordinates are just shifted from here to here. And we just use that and consider that to be this box here. We don't actually create many boxes. We're going to artificially create a copy of one box and just move it around to all these different locations. And that way, we can actually sort of emulate the behavior of all these boxes. So I'm going to create just one box, or maybe 2 boxes that we had originally. And what I'm going to do is just move this one so that it's here, 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 here. And just calculate the interaction as if it were calculating all these different ones. So yeah, that way we can reuse most of the code we wrote here, because I'm just going to use this one, and then this one I'm just going to move to different places to calculate this, and then the step we used here I'm just going to move to different places to calculate this one. So let's see if that works, and because it's an easier code to write. So let's say xi, I'm going to calculate the same step as step 2. So where's step 2? This one. So step 2, I have xip, xjp. These numbers I can just change. So how do I do this? It's x. So xip is what now? Okay, 0.5 plus distance. So I don't need this distance thing anymore. I'm just going to reuse this code. Okay. So the part that changes is step 2, and also step 3. Step 1 is the same because we assume that all these all these boxes contain the same information. We just move them to the different positions. So step 1, we calculate for just one box. And then we assume that these are all the same. They contain all the same Q. So the Q is the same for all of these boxes. Now, when we calculate this one, we need to make sure that we move the red boxes to each position in this picture. So first, the blue box is here, and then we need to calculate for the red boxes that are far away, like in all these locations. And then the blue box moves here, here, gradually moves around, and the red boxes we need to find accordingly. So each of these boxes here, we need to assign. So let's okay, so it's the xi and yi, zi that change. So now it's all 0.5. They're both 0.5, 0.5, 0.5. But okay, I think this is done best inside a loop. So we go from, let's say, there's 4. Okay, but we need to move it in each direction, so it needs to move in like the x, y, and z direction. So x, in the x direction it goes from 0 to 3, and in each direction it moves. So it moves like this, it moves like z, z, z. Okay, so this is the blue, when you do this, what you're doing is this loop x going from 0 to 4 is the blue box is moving from, like here to here. In the y direction it's moving in this direction, and this z is moving in the other direction. And now what we have to do is we need to figure out how to move the red one. So there's going to be another 3 loops for the jx, jy, jz. And what we're going to do is we do like a if statement saying if ix and iy, or ix and jx are close or next to each other, then we do this one. If it's not, then we do the other one. So we just need to loop 3 times more for the j. So I'm just going to copy. So it's many loops, but each loop is only 4 times, so it's not very much work. I just need to make sure to change jx, jx, jy, jy, jy. Okay, so now we created 6 loops to find each of the boxes. And now, so we need to make sure the distance between ix and jx, so I think we need to take the absolute value. If this is So 1 is okay. If it's like a distance of 1, that means it's, no, I mean, we need to have this condition and IY minus JY less than 2 and IZ JZ less than 2. So this is the condition which says this, if it's this condition, that means it's near. Otherwise, it's far. Yeah, so this will give you the two necessary cases. I think you'll see on the screen, so this near and far that I showed in the slides. So if Ix minus Jx, and you're looping from 0 to 4, if these two numbers are either 0 or 1, this means it will be 0 or 1. If it's 2, it won't satisfy this condition. So if it's 0 or 1, it's inside this domain here, somewhere. And these are connected with the AND, because if either of them are 2 or larger, then they might be neighboring in this direction, but they'll be far in the other direction, so it's okay. They just need to be far in some direction. So unless they're this and this and this, they're not close. So if they satisfy this, that means they're close. We will calculate this near equation, but with the shift. So this is the amount of shifting that we can that we need to do. So we just need to add Ix to the x and Iy to the y, Iz to the z, or Jx to the x and Jy to the y and Jz to the z, j. So just do the calculation, the same calculation, but with the distance. So the distance is relative. So what we need to think about is just the difference between okay, so when we're calculating the near equation, we actually need to loop over all the points. So we need to loop over, I need to add, I forgot to declare the j. So let's loop over all the bodies inside I, the target box, the blue box. And then we also loop over all the bodies inside the J box. So now the code is getting quite wide, so maybe it's a little bit difficult to see. But okay. Maybe I can reduce the size of the font so you can see a larger screen. Okay. So now we're looping inside both boxes, all the particles inside each box. But now, when we calculate the distance, we do something special. So this is the standard positioning, but we assume that xi is like shifted by ix and xj is shifted by jx. So this is the actual distance that we're calculating. So same for y and z. So dy dz, we assume that they are shifted according to these values here. So the numbers that are ix, iy, iz, jx, jy, jz, these numbers are the amount. So this number tells you which box you're actually looking at. So if jx is 1, then xj is that much moved. And same for I. If ix is 3, for example, then xi should be moved 3. And because the distribution of these inside these boxes goes from 0 to 1, and these are in increments of 1, it goes from 0 to 1, and then 1 to 2, 2 to 3, 3 to 4, like we want it to. So, and same for this side. So we're just artificially creating this 4x4 size box and calculating the points inside them by assuming that each box contains like a similar distribution of x, y, and z. So it's sort of a fake problem, but we'll assume that they have the same distribution inside each box. Okay, so now we have the distance. We can calculate r from, where's the r? I'll just copy this one. I'll just copy over this calculation of r from these dx, dy, and dz. And from this r, I can calculate the ui, and make sure to add to the previous value because this is just adding. And qj, you don't need to add anything. This is just the charge. It's not moved, or you don't need to add any value, special value here. Okay, so I mentioned that in the previous example, all the points were far, so the r would never be 0. But in this case, since when for example, ix and jx, iy and jy, iz and jz are all equal, then there's one case when I equals j that this r will be 0. So we need to avoid this case, because otherwise we'll have a number infinity. So to avoid this, we can say if I equals j and even easier, if simply if r is 0, r is not 0, we do this calculation here. Okay? If r is 0, we don't do this calculation. Just to avoid dividing by 0. Okay, now we move to the, maybe I'll close this other window because it's easier to see. Okay. So now the other case, we need to calculate ui prime let's do so okay, this may be a problem. We can't say that ui is the same everywhere because ui needs to be different boxes. So let's see. So UI, when UI is different, we can't add to the same UI. Right now, we're adding to the same UI even for the different box. So we need to either create a different UI for each box, which means we need to multiply this by 64. So we need many UIs. The other values we don't need many, but just for UI we need many. Okay, now we need to add some number that represents which box we're looking at. So let's say I box is some function of ix and then iy times 4 and iz times 16. This should give a unique index for each box, because xy and then iy times 4 and iz times 16 is just one number that we can. Okay, so this will give you, and actually I can define this up here because it doesn't depend on other values. Okay, so this is the UI that we will use. And we can calculate the same way UIP. So every time we calculate UIP, we will overwrite the previous one because we don't need to save the other ones. So for UIP, we need to initialize, we need to initialize this before we loop over the J boxes. Okay. UIP, and then we need to add this to all the boxes. So now, since we don't have unique particles to deal with, we don't need this xi thing. We can just subtract the center coordinates from each other. So for the approximation part, we're just dealing with the center of the boxes, these things here. So it's actually ix minus jx and iy jy and iz minus jz. And that will be the distance between the center of the box. And then for r, we calculate the distance, and then QJP we can reuse. So QJP is the same for all boxes. It's 10. And then we calculate the UIP from all the J boxes, all the red boxes. So that's why it's being accumulated here. It's because there are many red boxes for each blue UIP that we are calculating. And then once, at the end of this triple loop over all the J boxes, we will have one UIP that needs to be added to the UIs that we calculated earlier. So we have a loop for, over all the UIs, and we say UI, we add the UIP to the UIs. So we say UI add UIP. So this is actually step 3 done for each box. Step 3 is being done. Oh, sorry, I need to add I box. So I box was the index that we determined here. It's a unique index for each box. It's being used here in the direct part, and it's also being used here in the far field part. This is step 3. So, and this one is step 2. Okay, so I think now this should give us the whole solution. So that wasn't too much modification. I just took the original code and added all the loops for going through all the boxes. So step 2 became very long. But the real step 2 is actually this part here. And this one is step 3. So we don't need this step 3 anymore. This is the step 3 is done inside the step 2 loop. Okay. Now to check the answer, we also need to loop over all the i's, the different I box and j boxes. So we need to have this triple loop over the, like this. And I think we also need this I box here. And we also need the j box loops, like these 3 loops here. Okay, and let's see, which order should we do? Yeah, maybe we can take the I loop in front of the all the j loops. So these. Okay, like this. So now we have the loop over ix, iy, iz, and then loop over I, jx, jy, jz, and then the loop over j. And UID is a direct solution that is calculated. So now we need to change this part again to add the ix, iy, iz, and the minus jx, jy, jz. And then this should give you the correct answer at all the points. And this should be compared with, so if I print this, it's going to print many numbers. Now we have 64 times more numbers to print. So maybe I should restrict the number of prints, but this I plus I box compared with UID should be the comparison. Okay, so now I will use my screen to execute on the okay. So I'll run this now. Step 2. Okay, it's printing many numbers and they seem to be okay, there's one number that's very different. Okay, yeah, there's something not working with this one. Maybe I forgot to initialize.
Excuse me.
Yes.
I think there are some index, iBox index, and they should multiply by n.
Oh yeah, you're right. This one. Wait. I need to have the whole thing multiplied by. Okay, now let's see if this is step 2. Oh, good. Now, now they're matching much better. I don't know if this is the limit of the accuracy. Yeah, this looks about right. Okay, so what just to summarize what I did, and I'll make sure to show you the code while I'm explaining that. Oh, no. So you can see here in step 2 what I'm doing. Maybe if I make the code even smaller. Can people still see this? Yes? Because I want to show as much of the code as possible. Okay. So just to explain what's happening. So what I'm doing is all these loops here are looping over each direction one at a time. So it's looping over all 64 4 times 4 times 4, all 64 boxes. And this 3 loops for the I is moving the blue one. This 3 loops for the J is moving the red ones. So instead of finding blue and trying to search for the red that corresponds to this, I'm looping over everything against everything, and then using this if to determine which one it is. So I'm not doing the near one and then the far one. I'm doing them both at the same time by looping over everything against everything. And then this determines if it's near. Because if Ix and Jx are smaller than 2, that means they're either 0 or 1. That means they're either here, here, or here. And in the y direction, they're either here, here, or here. So if it satisfies this condition, that means it's close. So how I do the near calculation, I do the near calculation by looping over all the points inside the blue box I, this part here. And then looping over all the j, one box at a time. So it's only n, but they loop over all the boxes eventually by looping through all the boxes. And then I need to move the points because this xi, yi, zi, xj, yj, zj, I specified in the beginning to be between 0 and 1. So all of these numbers are still between 0 and 1. And so they would be in like the corner of this upper box here. Or no, the lower box here maybe. If you define this to be the origin, then you need to shift them according to the movement. So there's a minus sign here, so I have to put a minus sign here too. So Ix shifts the I boxes and the I particles, and Jx shifts the J particles. So it takes all the points here and moves all the points. And so when you take the distance with this value, you actually get the distance between, for example, this one and this one, this one and this one, between the boxes. And then you just calculate the distance and take, since Q is assumed to be the same for all the boxes, and they're always 1. So you can calculate with this. But the problem was this UI. So I was originally thinking you could just accumulate everything into UI, but it turns out because UI means different things, UI for this box should be different from the UI from this box, and it should be different from here. So I had to make sure that this doesn't overwrite every time to a different box. So this I box, I made it so it returns like a unique index for each box. So xi, yi, iz, one combination returns a different number from others. And because I didn't have this n, it was originally incorrect. But because I'm adding it to the UI, each box number should be multiplied by the number of points in each box. And then this is like an offset for each of the boxes. And I'm looping over I, but it means different boxes every time the I box changes. And then if it's far, all I need to do is, there's no xi and xj here. I just need to calculate the distance between these two. And since I know how much I'm moving the box, the distance is just the relative positioning between the two. So if this is 1 and this is 2, the distance is -1. It should, and if this is 1 and 3, this distance should be 2. So it's the same thing. I calculate the distance, and then I accumulate that into UIP. Say, you see that I'm initializing UIP here. This means, because when it's inside these 3 loops, I'm looking at the same blue box. So initializing here means I'm refreshing the UIP for here, and then I loop over all the red boxes with these J loops, and each time I find one that's far, I accumulate. So this will allow me to accumulate for all the red boxes, because I'm looping over all of them and determining which ones are far. This will accumulate all the necessary UI prime to this point. But now I need to make sure that this goes into the proper UIs. So then the only thing I need to do left is to do this. So the UIP that I calculated here needs to go into the proper one that's offset by I box. It goes into the UI, and it's being added. So UI is already calculated here. All these are being added, and to that I add also this effect. So now you have the far effect being accumulated into UI here, and the direct effect, the near effect, being accumulated here. So by doing this, you are able to calculate all the necessary UIs for this calculation. And now, for checking the answer, it's actually doing something similar. So we loop over all the boxes against all the boxes. This time, I assume that everything is near. I just use near for everything. So there's no if statements. And I do the same calculation that I do for the near calculation earlier. And I use this, oh wait, so why is this R not 0? Because I'm using different random numbers for xi and xj, they never become the same, actually. So yeah, I didn't have to do the R equals 0 thing, because you remember in the beginning, the very beginning, I used a different DRAND. So here, if I used xj equals xi, yj equals yi, zj equals zi, then I would have to worry about R becoming 0. But since these are generated from different random numbers, it actually looks like for the I blue boxes, the particle distributions are different. So it's actually not doing the the same interaction as I showed here. It's doing something slightly different, but it gives you the idea of being able to calculate the near-far decomposition. It's still, the concept still works in this code. So I think we covered what I wanted to do for today. It's basically, I wanted to have something that can calculate the near and far decomposition. To do this properly, you need to know the things I will describe tomorrow, which is like the how to construct the tree and how to bin the particles into each of the boxes. These sort of data manipulation techniques I will describe tomorrow in the lecture. So once you can do that, I'll write a much cleaner code for this one. But for today, you just need to do some artificial or fake way of doing this interaction between the boxes for the near and far field separately. So conceptually, we see that it's working. If you look at the numbers that was returned, it's, where did it go? So I'll just run again. Yeah, so you see the numbers are quite similar. They're like 200 something. If you go up, yeah, they're all very similar numbers. Yeah, okay, so you have these, but with the current first order approximation, this is the limit of the accuracy that you'll probably get. So the first number might be matching, but the second number will not be matching. So when you introduce the multiple expansions that I described later in today's lecture, you can increase the accuracy of this one. But for now, I think this is a good first day. If we can do this much in the first day, then we have 4 more days. So I think you can do a very fast calculation in the last hands-on. You'll have a very fast code by then. So today you don't have to worry. Just I'll make all the slides and the codes available anyway. So you can review them and make sure that you sort of understand the concept. But from tomorrow we will work more on the data structures so that you can easily calculate things like this. So how to find, just to give you a heads up on what you'll be seeing tomorrow. So tomorrow is the tree structure, and so there's a specific numbering scheme that sort of uses a space-filling curve, either the z-curve called the Morton index, or the one that looks like this is called the Hilbert index. This allows you to number the whole space, even if it's in 2D or 3D. It just gives you, if you know this number, then you know where it is in the space. So from this number, you can grab the information you need. So this was this thing that was missing today. But once you have this technique, you can grab any box anywhere just from this one number. It's like a address in the 3-dimensional space. So from tomorrow, we will discuss a bit of this data structure. Once you master this data structure, it's very easy for you to find what's close, what's your neighbor, what's far, what's your parent, what's your child. And so this freedom gives you a lot of, you can do this in different ways, but I'll explain tomorrow. You can use like structures that have parent and child and multiple inside them, or you can use like a one index to determine the parent. You don't need a pointer. You can actually do this through division and multiplication to find the index, and then you can grab it explicitly. So many ways to do this, and I'll describe this tomorrow. But for today, I think we are finished with the hands-on. So thank you. Oh, questions? Yeah. If if you have any questions, well, we can continue if you want. How long is this room open?
I think you'll keep
You can.
opening.
Okay.
So
So
if
yes.
you want, you can stay here. Yeah.
So
So
yeah, I can continue looking at, you know, if you weren't able to follow the code, you can stay a bit longer, and I can take a look at your code and see how to, you know, help you make it work before you go. So yeah. Okay. So but if you're all finished and if you're satisfied, then you can go to lunch. So you said we have a lunch here?
Actually, outside we have a lunch box here. So
Okay, we have.
you can
Okay. So you can, so that means everyone can stay.